Hello, my name is Mohammed Amjad Khayyam, and today we'll from Team Jam, and today we'll be talking about determining the optimum location for the direct air capture facility in Alberta. The global warming is one of the major issues that the world faces due to a rise in atmospheric carbon dioxide due to human-based emissions, which is responsible for about two-thirds of the global warming effect. And an increase in this carbon dioxide levels will lead to increased global average temperatures, glacial melting, and ocean acidification. So in order to combat this issue, Canada's goal is to achieve net zero carbon dioxide emissions by 2050, as per the Net Zero Emissions Accountability Act in 2021. CCUs are an essential solution to enable Canada to meet this goal, and direct air capture, or DAC, is an effective technology in order to remove carbon dioxide from the atmosphere. The benefits of DAC are many. It captures carbon dioxide directly from the atmosphere, allowing for the removal of previously emitted carbon dioxide. One DAC unit can capture about the same amount of carbon dioxide as 45.5 million trees in just a fraction of the space. And they are a viable pathway to negative emissions, and they offer a pathway to offset emissions from hard to decarbonize sectors such as the cement industry and the transportation industry. There are three main types of processes for capturing carbon dioxide using DAC. It's chemisorption, absorption, and adsorption, and these are the materials used for those. And each method requires different climate conditions. Chemisorption and absorption basically requires high temperatures and high humidities, whereas adsorption requires the air to be dry and the temperature to be low. So since Canada has a dry and cold climate, adsorption-based methods are best suited. The zeolite NaX was chosen as the adsorbent to capture carbon dioxide due to its low cost and commercial availability, its high stability, high absorptivity, fast uptake rates, and a low heat absorption. The following assumptions have been made. It is assumed that the facility will have a dehumidifier to remove the humidity from the air, so that the capture process is very efficient, and the values for absorptivity for NaX are based on the carbon dioxide concentration in the air being 420 parts per million.
Anyway, some of the data assumptions that we also found is, we didn't tune our machine learning model as much as it should be. That takes weeks of engineering effort. You just need to spend that. Proper solution would spend more time on the validation. We also probably could have considered not using the residuals in a seasonal decomposition. Using the seasonal aspect might increase accuracy. We didn't explore that possibility in this analysis, but that's totally a possibility to increase accuracy. We also assumed a constant rate of climate change, so assuming that the historical trends of how the climate is changing is accurate. It's very possible that the climate changes faster, but we're assuming that it's just the same. Just in general, estimating absorptivity based on location like this, assuming that's correct to do, that might not be a proper approach. And also, like we said before, we assume a pretty constant carbon density in the air. And as for our methodology, we found a metric for absorptivity versus temperature. We found our temperature data. We trained an XGBoost algorithm to predict points, and we're predicted out 30 years. We also found, based on that 30 years, we calculated an average temperature, and then we used that to estimate the estimated absorptivity of a location, and then we used the max function to find the best location.
To find the absorptivity was temperature. The temperature versus absorptivity in millimole carbon dioxide absorbed per gram of adsorbent was found based on literature, and that was converted into milligram carbon dioxide adsorbed based on the molar mass of carbon dioxide. And then it was plotted again in a graph, and a linear equation was obtained, which was then further used.
Yeah, and then further along, we basically use this township viewer to download points of specific historical time series data of temperatures. We basically were able to find something that converts the data format of this viewer to lat-long coordinates, cleaned it up a little bit, and then from that, we were able to use this natural Earth data set that basically converted lat-long to nice visualizations for us. And we found states specifically, so we could do Alberta. And then here you can see us loading in the data. Here's Canada. And then, yeah, we were able to plot our samples we took from the data onto our map here. And then based on every sample we took, there was a time series data set. So here's like a brief view of all the different data sets we had. Then we ran some seasonal decomposition on these data sets. So specifically, here's a season period of a month, 4 months, 12 months, which starts to get a lot better because we start seeing that like there is more of a trend and understanding of what the temperature is. And then 24 months is what we ended up using for our final product here. Then what we did is we ended up converting the data from kind of a pairwise format so that we could make a model that predicts current state to new state kind of thing. And we trained an XGBoost model on this. So you can see that we have our expected predicted here. And then from that, for all 48 of our townships, we ended up just like batch processing that. And then using our equation, like our projection of absorptivity, we use that to make a average predicted temperature in the next 30 years column on our data. And then from that, we were able to do a graph where we can see the various sites on their suitability for carbon capture. And specifically, you can see the later things are better, and we have a single point that's good. But yeah, our data's on everything's on this GitHub, and please install this specific installer if you'd like to like try running it yourself. And then we got 30 seconds for future work.
So the once we capture the carbon dioxide from the stack facilities, we can permanently sequester capture carbon dioxide by injecting them into tubes and the current geological formations. And we need to find an optimal site for this one. We take into account reservoirs and rock property, underground properties, make sure depth of formation as well. Once this criteria is met, you can conduct the capacitance and injection.
Anyway, thank you for your presentation, and we hope we hear from you soon.